So just like with the Laplace transforms, we frequently need to find the inverse Fourier transform, and we do that not by using the mathematical definition, but by looking up on this table and finding the given f of omega that looks closest to what we're given, and then reading out the corresponding f of time. So let's give an example. Say we're asked to find the inverse Laplace transform of omega squared over omega squared plus 16. So that's our f of omega, and the question is, find the corresponding f of t. So we begin by looking down here and trying to find the one that looks closest. Now, there's nothing that looks like an omega squared up on top. I know that already. There's nothing there. But we can find ones that look like this omega squared plus a number. Here's an omega squared on the bottom. Here's an omega might be able to, oh, this looks perfect. Omega squared plus a number, but there's no omega on top. So this is the one we're going to try to use. Recall from Laplace transforms that when there was an s squared on top and an s squared on bottom, you did long division to simplify and to get it into a proper fraction. Same thing here. The first step is always determine if you've got a proper fraction. And now since it's Fourier, we're doing it in omega instead of s as we did for Laplace. And if it's not proper, if it's improper, we're going to use long division. Just like in Mrs. McGillicuddy's 8th grade classroom, you'll do that division. And you'll see omega squared goes into omega squared one time. Instead of subtracting, I think it's easier to add and then negate those things. So it's 0 minus 16 gives us minus 16. And that leaves us with a remainder of minus 16 over omega squared plus 16. So now the question is, can we find the inverse transform of 1 minus 16 over omega squared plus 16? Now it looks really close to this on the right, with a squared being 16. So that means a is 4. Problem is that 2 times 4 is 8, and that's not 16. So using the standard way that we've been doing this a lot, if we had this, then we could directly read off its transform because a is 4. But this isn't this, so what do we need to do to this to make it this? What do we need to do to 8 to make it 16? We multiply it by 2. And now we can find the inverse transform. Now the inverse transform is the inverse transform of 1, which here is a unit sampling function, minus 2 times this exactly reads onto this with a being 4, so therefore that's the same thing as e to the minus 4 absolute value of t. And that's the solution. Least you thought I was going to let you off that easy with just one problem for inverse Fourier transforms. Let's do another example. We said that the first step was to make sure that f of omega is a proper fraction before finding its inverse using tables. And if not, do long division first. And that's a proper fraction in omega. The second step is that you may need to use partial fraction decomposition, just like you did in Laplace transforms. Instead of using partial fraction decomposition using j omega, firstly substitute s for that j omega, and that'll simplify your algebra. It's a lot easier writing s than j omega all the times. So just do that substitution, and it's only to simplify algebra, but it's also because you're used to using partial fraction decomposition using s's, so this will also make it the whole process more familiar to you. Here's an example. You've got 10j omega plus 4 over minus omega squared plus 6j omega plus 8. And the question is, find its inverse transform. Temporarily, to give us some space, I'm going to move this table off our screen. And let's do that first substitution to make our algebra simpler. So that would be 10s plus 4 over, now here's a problem, how do we get minus omega squared by substituting s for j omega? We'll realize that j omega squared is equal to j squared omega squared, which is minus omega squared. So whenever you see a minus omega squared, that's your clue that it is in fact the same thing as j omega squared. And so that's the same thing as s squared. Plus 6s plus 8. So now we've transformed this into this more familiar looking device. Check to make sure it's a proper fraction. It is. The greater power of s is in the denominator. See if you can factor that by inspection. So that's s plus 2, s plus 4. That numerator is still 10s plus 4. So partial fraction decomposition says it must be something over s plus 2 plus something over s plus 4. Let's use the cover-up method. We'll take the s plus 2 term first. So we'll cover up the s plus 2, pretend it's not there. So since we covered up the s plus 2 term, we're going to substitute in its corresponding root of negative 2 to find out what the numerator is. So negative 2 up here gives us negative 20 plus 4 is minus 16. Negative 2 down here gives us 2, so that's minus 8. Here, we'll cover up the s plus 4 denominator part. And so now substituting in the root of s plus 4, which is negative 4, we get negative 40 plus 4, so that's negative 36. Over negative 4 plus 2 is negative 2, so that's 18. So now we have negative 8 over s plus 2 plus 18 over s plus 4. I think it's time to bring in our transform table again. Looking down our transform table, I realize I didn't convert this back into j omega. So that's negative 8 over j omega plus 2 plus 18 over j omega plus 4. So going through here, yeah, that's definitely this guy. So that has an inverse Fourier transform of f of t equaling negative 8 e to the minus 2t plus 18 e to the minus 4t. And you'll notice that all of that is multiplied by u of t. In summary, when you're doing the inverse Fourier transform, it works the same way as the Laplace transform. Remember to begin by making sure that it's a proper fraction, and use partial fraction decomposition if you end up with a complicated polynomial. If you don't end up with a complicated polynomial, you may be able to find its transform directly in this column. Now I'm going to take one more step with this problem. Take a look at that term. What would happen? What would happen if we made that term not 18 over j omega plus 4, but what if it was something like 18 over j omega minus 4? Now that's something that you haven't seen before in Laplace diagrams, because that would be the equivalent of 18 over s minus 4, and that would mean that your pole was in the right half plane. You'd end up with a e to the positive number, and it would be unstable, it would grow, and something would be wrong. But in Fourier transforms, that's perfectly allowable. Take a look now in the Fourier transform, going down here, and you'll find the transform right here. The only problem is, once again, these two don't look exactly alike. We'd have to change that into 18 over, so we'd have to multiply the top and bottom by a negative 1. So we'd have minus 18 over 4 minus j omega. Now it looks exactly like this. So therefore that has a inverse transform of minus 18 times e to the positive 4t u of negative t. And if you're alarmed by the presence of that 4t, that seems like it's a growing exponential, you needn't be. If you were to graph that out, that positive 4t is only active because of this negative t for time less than 0. So in other words, for time greater than 0, we get this, it's 0. For time less than 0, this u of negative t becomes 1. And as t gets more and more negative, this e to the 4 times negative t decays down more and more. So it looks like this, except that it's a negative 18, so the whole thing would be then scaled. This would be an example of e to the 4t u of negative t. And so the thing altogether might look like this. And that might be negative 18 e to the 4t u of negative t, where it would dip all the way down to negative 18.